let's draw our diagram again. Okay, so this is my VA applied across delta. I am assuming a delta gap excitation. Okay, let's call this Z equal to 0, and second antenna element over here spaced apart by D, but it's parallel to each other. This center is at ZB and the length is minus LB by 2, LB by 2, LA by 2, LA by 2. Alright, geometry is clear. Length LA, length LB. Current is IA, current is IB. Okay. Now, in the single antenna case over here, if you remember, what I had done was that my current source was along the Z axis and I had taken the observation point to be this radius apart, A apart, right. That is why this A squared was there. And we had done this to avoid what? The Green's function singularity. I could have chosen the points to be on the same, on the surface of the antenna, right, it is possible, and we have dealt with singular integrals, right. So, this, but to make math simpler, we had done this to avoid singularity. Here, however, there is a certain symmetry is missing over here, because I mean the second antenna is on one side. So, I cannot, in good I mean being honest, I cannot take some distance A apart and do testing on that point. So, here what is my sort of alternate, what is the solution that I will do for source points and testing points? Remember, here this was my source and this was my testing point. So, here I have no choice, I have to live with the singularities. So, I will where the current is flowing, that is going to be the place where I will do testing. I will get a singularity in Green's functions, I will deal with it, okay, not a problem. But now let us start with the boundary condition, okay, that is what is going to guide us. So, let me rewrite it. Boundary condition is, for example, equation 1, right. So, equation 1 will give me EZ SA Z plus EZ SB Z is equal to minus EI ZA Z. Now, let us just do a one-to-one mapping of this. What will the first term become? So, this is our shorthand notation for the left hand side. So, integral from where to where? This is the field due to the induced current on the same antenna on A. So, what should be the limits of integration? Minus LA by 2, LA by 2, very good. Which current will this be? IA or IB? IA, okay. Z prime, so let us say Z prime is the coordinate that goes up and down over here, okay. K of Z prime, dz prime. This is the field produced by A, the scattered field produced by A, excellent. Next is the field produced by the current induced on antenna B. So, limits of integration? Minus LB by 2, correct, LB by 2, I B, okay. To make life more clear, I will say some other coordinate, because this is a dummy variable, but let us make it a different symbol, and K of Z, Z double prime, D, Z double prime, okay. This Z prime, Z double prime is the relative coordinate on, means relative to ZB, okay, is equal to minus EI ZA Z, right. So, this we are assuming for example a delta gap or whatever you want, does not matter what it is. That is my first equation. second equation becomes, second equation would be coming from which boundary condition? This guy. The only difference is, so over here, one sec, so one thing I should make clear here, Z belongs to which place? This boundary condition is valid for which Z? A. Z belongs to A. Now I have to take Z belonging to B, right? So Z belonging to B, first term is the field produced by the current on A falling on B, right? So this is going to be limits of integration minus LA by 2 falling on B, that's all right. So my Z is going to be on B, but Z prime has to go over whichever current is radiating, right? So this is going to be LA by 2 IA Z prime KZZ prime DZ prime, okay, plus second term is the self current equal to 0. Right. So this is the expression that you should try to interpret. What is this saying? That the left hand side, just look at the left hand side. What is the left hand side saying? I will tell you what is the field at any point Z if I carry out this integral, right? Z prime runs over the current element and Z is where it is, and I am matching it on the boundary by equating it to minus E incident. That is the meaning of this, right? And remember, how did this thing come? It came by convolving G and the current, which gave me A. From A I got E. So this is the value of the electric field at any point Z, and to solve it I am matching it on the boundary. So similarly, this is the field produced by the current element A at some location Z. This plus this is what is being made equal to either 0 or the incident field. Okay. Both IA, exactly, right. So IA, that is what I want to find out. IA and IB are unknown. K is Green's function with this operator, right. This, remember, d by dz square plus k square acting on G, that is what is my K. It looks complicated, but it can be evaluated. Okay, so we are almost there. So let me put a few subscripts here. This K over here, this is A on A, right. That means the source and the testing point were A and A. In this K, what is the source point? Source point is the second element falling on A. Here, what is the source point? A falling on B. This is B falling on B, right. So the notation was K source to observation point. That is the interpretation, right. Just otherwise everything looks like K, but in fact the Z and the Z prime correspond to the source and the destination. So what is the source and what is the destination? That is to make it very, very explicit, right. So in K A to A or K B to B, I have a Green's function which has a R. So what will that value of R be? Z minus Z prime squared or Z minus Z double prime squared, because it is the self term. And in K A to B or K B to A, what is my R over here? Remember, the distance is D, so it is going to be a D squared. So basically one point is over here and the other point is, let us say, over here in K A to B or B to A. So I will have a D squared plus something like Z minus Z B plus Z double prime squared. I have to just find out the relative distance between, right. Z double prime goes from minus LB by 2 to LB by 2. It is offset by some value ZB. So, this is the absolute Z coordinate on current element B, and current element A was anyway on the Z axis, so it is just a Z, right. So, this is the this distance. So, I mean it is not complicated, I just have to keep geometry very carefully in mind, and this whole thing over here will boil down to a coupled matrix equation. This first term over here, so what is unknown over here? IA and IB. So, IA for example, so this whole thing can be written as say some FAA, FBA, or let us call it AB. BA makes sense because source to observation, then FAB, FBB. Once you calculate all the matrix, I mean the integral IA, IB is equal to H and 0. This is after the MOM procedure has been carried out. So, what will be the size of these submatrices? So, F are all submatrices, FAA are submatrices. What will be the size of, for example, this or this? Yeah, so this will be NA cross NA, right. Similarly, this will be NB cross NB, right. So, this overall matrix is of what size? NA plus NB cross NA plus NB, because I have discretized A into NA elements, B into NB elements. So, I get a bigger matrix and I solve it. Yeah. After having done all of this, what was my objective? I have done all this great math, I have got some solution, I have solved it, got IA, IB. Now what? What was my original objective? Driving point impedance. How do I find that? So, I want to find out, for example, ZAD equal to the grand question. H is whatever is coming from the vector form of this guy is what is coming over here at all the testing points. ZAD then becomes, at which point am I asking this question? At the connection terminals of antenna A, that means at this point, right. So, voltage A divided by what? That is all. And why is it all? Because IA is not the current in the absence of the other object. IA is come as a solution of everything, all the mutual coupling has been taken into account. So, I don't, it is slightly different from this circuit model where I need to first find out Z11 then Z12 and the ratio of currents. Here I am directly solving this problem, finding out the current at the input terminal, that is my driving point. So, you could find out the mutual coupling by solving the problem without element B, you get some impedance, right. So, this sort of completes how to deal with two antenna elements, and this opens up a vast area of research. I will just very briefly mention it over here. Instead of element B being a current element, you could have, for example, a human body, and you wanted to study what is the role of a human body on the input impedance of your antenna. You are holding your mobile phone over here close to your head, it is inducing some currents on your head and changing the input impedance, right. So, everything inside the antenna will change depending on what object you place it close to. So, people have used this as a model for not just like a one wire element, but make it a complicated object, find out what is the mutual coupling over there. Okay. So, in general, electromagnetic problems are very challenging because of these induced currents floating around everywhere, okay. And this is one rigorous way of dealing with it when the geometry is very general, need not be some very specific thing, okay. And this procedure can be generalized to as many elements as you want, and like an antenna array. Okay. So only thing to be careful about here is that we will have to work out the Green's function with the singularity, because I am choosing the source and testing points to be along the same axis. 3D Green's function. Like this is like our original problem over here. This was my 3D Green's function, no? So the current element is one dimensional. Well, actually it's it's one dimensional. It's only along a finite length along the z axis. It's very thin in radius, but it's radiating in 3D space. That's why I'm using the 3D Green's function. And making the simplifying assumptions of z directed and very small radius, that volume integral boiled down to a line one dimensional integral. Just because it's one dimensional integral, you shouldn't think that it's a 1D problem. It's a one dimensional element radiating in 3-dimensional space. So as long as your wire is very thin, this is exact.
X, Y, and Z.
Yeah, that's where this a square comes in. Yeah, what I wrote was for this, what the z minus z should have. Yeah. Yeah, so you are right. So this, instead of z, this should be zb plus z double prime. That's what you are saying. Actually, yeah, we have to move to the relative frame of the antenna element. So yeah, even the original thing is fine, as long as you are sure that z and z prime are in the same. If z is also on the current on the axis and z double prime is also on the same axis, there should be, the singularity should be there.